Okay, so today our goal is to finish the conditional inference tree training exercise, and then we'll also most likely start and finish our random forest exercise as well. All right, so starting with the conditional inference tree, if you don't have your project open yet, go ahead and open it. Let's see, so I think we stopped. Let me just find here. Yeah, I think we stopped at checking these plots here of the grid search iterative process. Um, so if you have your environment empty as I do, we're gonna have to recreate some of the objects. I do not want you to just run all above, because if you do that, it's gonna run the grid search again, and that takes a moment. So to make sure you don't get stuck on that while we keep the exercise, let's just run the objects that we really need to run. So of course, loading our packages, importing the weather object. On the weather split, we want to go ahead and do that as well. We want to create weather train and weather test. You don't have to recreate this plot. We want to create our recipe again. We want to prep the recipe on the training data. We want to do our CAT spec object for this specification. I think that here, let me see. So we would have done the training normally, right? Which really the step that takes time is when we do the two simulated annealing function. However, since we've already done this and we already identified, or actually we have not identified our best combination, I think. Yeah, so maybe we're gonna have to rerun it just because we did not do the last step here, which was selecting the best model. All right, so let's just go and do that. Let me just go back. The last thing that I ran was the CAT spec. So we're gonna have to run the resampling strategy. So setting seed and then resampling fold CV object. Again, I just want to perhaps reiterate one of the steps here, that for CAT, of the models that we trained up until now, which have been only two, CIT has a hyperparameter that we're fine tuning at the level of the engine, whereas ElasticNet had all hyperparameters that we were fine tuning at the level of the model. So because of that, we have here for the CIT, we have this extra step of creating CIT param, so we can update the range of values of the conditional mean criterion that are going to be fine-tuned. So that's a difference. Again, just taking one step back. And if we look again, I'm going to go above here just to show you what I mean. If we look again on the code on the CIT spec, the decision tree function is the model type we're using. And notice that we have tree depth there, and we're asking to tune it. Now, decision tree is a general function for decision tree models where PartyKit is one of the engines. There are other engines. Because PartyKit is one of the engines and conditional mean criterion is only is a hyperparameter that exists at the level of the engine, then we're specifying that hyperparameter here on the engine instead of putting it on the decision tree level. So that's one of the differences that we're seeing with CIT. And I just wanted to make sure you understand this, that sometimes you have hyperparameter values that are applicable to the model type in general, regardless of the engine. And other types like here, we have some hyperparameters like tree depth that are applied at the model type level, but then we also have engine-specific hyperparameters like conditional mean criterion for party kits. So that's why in this case, we have one hyperparameter at the model level, one at the engine level, and because we have one at the engine level, we have to do this extra step of setting or updating which levels of that hyperparameter are being evaluated on the search. All right, so I think this is the chunk that takes a little bit of time. I'm just gonna run it. And also I wanna show you here a trick that I use sometimes when I know a chunk is gonna take, it's not gonna be like a second run, it's gonna take a little bit more time. There's a package you may not have installed, but it's called Beeper, Beep-R. If you just run that, it's just a beep. But then if you play the whole chunk, once it goes through the part that really takes time, it's gonna beep for you. So you don't have to be watching your chunk. You can just start running and then do other things. And when you hear the beep, you know that is done. So that's what I'm gonna do here. Just go ahead and play this chunk. And also I think it's gonna be interesting for us to notice because last time we ran in class, I gave you a break. So you were not watching the action happening. So now we can see here that it is each number here is one iteration. We ask for 50 iterations where it is searching that grid iteratively, where it was able to find a new best combination of hyperparameters at iteration 5, at least for me. And then it keeps searching it. So see that the current best at iteration 5, we have an RMSE of 3.0034. Then it keeps doing that simulated annealing search. And it found a suboptimal result on the next iteration, meaning that the RMSE did not decrease. It found still suboptimal. If it keeps finding suboptimals, meaning that it was not able to further reduce RMSE with other combinations of tree and mean criterion, at some point it just restarts from the best because maybe the iteration went on a direction of the grid. Oh, it was actually pretty fast. In a direction of the grid that was not right. So it kind of resets on the last best and keeps going. And so at least for me here, let's see, it really found the best on iteration 5 and it was not able to find a new best after that point, as you can see. And with that, it just takes the new best and returns that combination of number of trees and mean criterion or tree depth, not number of trees. Sorry, I'm thinking of random forest already. Tree depth and mean criterion for us. And again, we're doing 50 iterations because we're doing this in class and we don't want to spend a lot of time waiting for this. But if it's for your research, I would recommend at least 100 iterations and make sure that you give, especially if you're doing the iterative search, because each iteration is another chance for a model to visit a different space of that grid and potentially improve model performance. Okay, so we had done this step already, so I'm not going to talk much more about it. Just keep going. So we collect the metrics across all the folds and then checked the path, right? And again, I know some of you were getting paths a little bit different from mine. So I guess we're gonna see how when we pull the actual models that created these paths, we're gonna see what we get from it if your result is similar to mine. But here we see that iteration 0 started all the way up here with a mean criterion of around 0.992 perhaps, or 1, and a tree depth of maybe 10, I guess. Yeah. And then it was just navigating to this side of the space, to the right side of the space, and just iterating around this. And you can see here, so iterations 44, 45 may have been when the model went in that direction, but then notice, okay, I'm not improving here, let me go back. And so that's where we see the navigation of those iterations over the space. And this was for our RMSE, and we colored the points according to the RMSE value. If you remember, our MSC is we want to minimize this. So the lowest value that we were able to find is the 3.003, which is the purple color. So just by eyeballing it, it's probably somewhere around a mean criterion of really close to one, maybe one, and a tree depth of 3. So 3 horizontal layers of a tree. Then we also checked for our square already. Let's just run the plot. I mean, the path is exactly the same. At least it should be the same for our MSC in our square, because the path is representing the values of the hyperparameters themselves, right? What we're visualizing as color now is our square. So we want a higher value of our square, meaning that that was a better fit. And it seems like we got to a very similar place that was optimized, in this case, increase our square compared to our MSC. So it looks like still very close to one value of mean criterion of 1 and tree depth of 3. All right, so this is the point that we stopped from last lecture or last lab. And just to draw a parallel here, so when we were doing this step with the ElasticNet model, we use the function that I think is called select best, if I remember well, which basically just looking to one of the metrics, you could choose based on our MSC or our square, and gives you the model that had the best metrics. So if you're looking at our MSC, the model that gave you the lowest RMSE, and which hyperparameter values are associated with that model. Now I want to show you, we could also use the select best here, but I do want to show you a slight variation of that, which is going to be to select by one standard error. Meaning that you may have, so we evaluated, I mean, basically, if you think about it, the number of models we evaluated is the number of iterations that we had. So we evaluated 50 combinations of conditional mean criterion and tree depth. Maybe out of those 50, maybe there were, I don't know, 4, 5 models that numerically one of them was the winner, but statistically, maybe the top 5 were all very similar. And if you have the top one model having the best, let's say R square, but it's a very complex model, maybe if you go within model 2 or 3 or 4 or 5, they're still within one standard deviation or standard error of the model metric, you could get a simpler model that doesn't lose a lot of predictive power. So that's what this function is doing, is just trying to get the best within a given standard error of the fit metric. So if you start coding with me, we're going to use give it a pipe. We're going to use a function select underscore by underscore 1 standard error. We need to specify here 2 things. So one of them is standard error of which hyperparameter. I want to do tree depth. So we need to say what is the name of the hyperparameter. And then the next thing is which metric I want to use to evaluate this. In this chunk, our metric is going to be RMSE. So if we run this and we get the results, we get a tree depth of 10 and a conditional mean criterion of 0.99. Remember that thinking inversely here, if you do this minus or 1 minus this gives you the p-value that the model is using to allow a variable to enter the model. Did you all get a similar answer?
No.
Okay. Well, maybe it's easier to ask who got like the same results. Nobody. Beautiful. All right. Okay. Yeah. I mean, there are some randomness to this process, and I think that is what's causing some differences across us all. But yeah, for now, let's just pin that, and we'll talk about what we're going to do in a second here. But let's go ahead and do the same thing, but now looking at a different metric. So as you remember, it could be that RMSE and R square give you the same combination of hyperparameters that optimize both metrics. It could be that the case, but it doesn't have to be that way. Maybe our MSE tells you one combination is best, R squared tells you that another combination of hyperparameter values is best. So just to keep that in mind, and we're going to check that as well for our case here. So if you go on the next chunk, let's give it pipe. We're going to use the same function. So select by one standard error. Again, we're going to use the tree depth as our hyperparameter that we're evaluating for this error. And then the metric, in this case, we're going to change to be RSQ for R squared. So if you run that, I think in my case, I got the same combination regardless of the metric evaluated. So I got 10 and 0.9926. Yeah, so I got the same combination, but it seems like, well, let me ask, like generally ask this, even though your values are different from mine, but are your values the same for RMSE and R squared?
Yeah.
Okay, awesome. Yeah, it doesn't have to be that way, but when it is, I think it's nice because then it's easier to defend your choice. So I just wrote those numbers for me below here. If you want to write yours down here as well, that is going to help you. Because remember that, I mean, it didn't take that long to train this model specifically, but it could take a lot longer to train a model. So by you specifying those values here, I think that's going to help you with that. Okay, so I think I want to propose that we do the following. So here in the final spec object, we have the same code as before, where we have the decision tree function, we have the engine, and we have the mode. Now, notice that instead of saying tree depth equals tune and conditional mean criterion equals tune, we're actually given the values that we found in our tuned exercise that would just happen above. So I decided here, in my case, well, in all of our case, regardless if we use the best R square model or the best RMSE model, they were still the same hyperparameter values. But if they were not, then you would have to choose if you want to keep moving forward with which metric, with what hyperparameter values coming from which metric. If we were to decide to keep with the best R square, I just left here the best R2 $ tree depth, which if you run that, it gives you the number that we just found above. The same thing here for the mean criterion. So the best R square object, $ mean criterion, gives you the value right there. And this best R square object is the one here that we pulled the best model. So I'm just automating this a little bit more. You could just come here and write that number if you wanted. You could come here and say 10, which would be the same result. But I'm just using the object to kind of automate that a little bit more. If you run this actually sets the specifications of our final model. And that basically ends our training process. Something I want to call your attention to here is if you're not fully training a model, in the sense of you're not doing data split, you're not doing hyperparameter fine tuning, if you were just to come here and give this a number, a fixed number, but without knowing what was the best, just like, oh, I just want to have a model with a depth of 4. You could come here and do this. There's nothing keeping you from that. It's just that you didn't train the model. You're not specifying this value based on the training process. But there's nothing keeping you from that. You could completely skip the training step if you wanted. The code is not going to break, it's still going to work. It's just that we have the training phase because, again, that is what machine learning is all about, is you allowing the model to learn from your data what is the best combination of hyperparameter models. That's what training means. So I just wanted to bring that up here. All right, just going to make sure I rerun this in case I had not. All right, so now that we trained, so we know now what's the best combination of hyperparameter values that optimize our model predictive performance. Now we need to validate. Also, well, let me take one step back here and return above. I think it's going to be interesting if you all just go with whatever best tree depth and mean criterion you obtain on your side. You just need to be aware that maybe some of the results are going to be slightly different. I hope they would not be largely different, because then, we can definitely see that would be a shortcoming of this type of exercise, which, I mean, it could be anyways, but my hope, I guess, is that especially when we get to refitting. So, if you remember on the validation step, we do a few things. One of them is now using the hyperparameter values that we found. We're gonna basically apply this model to the entire training set. That has not happened yet. Why not? When we were figuring out the best value for hyperparameters, we were applying those combinations of hyperparameter values to each fold independently, meaning that each fold was basically being trained on 90%, because we did a 10-fold cross-validation. So each fold had 90% of actual training data and 10% for assessment. So up until this point, our final model has not been applied to the entire training set, which it happens at validation. So now we're going to see, when we do that, we're going to then get fit metrics for the training sets and for the test set. And I'm guessing those fit metrics are going to be slightly different from me to you, because we're using slightly different values of hyperparameters. So just wanted to bring that caveat, and for us to stay aware of that, because if your results are slightly different from mine, it's probably because of that. All right, so with that, we're going to do our last fit. So the last fit function basically does two things for us. Number one, it applies this last model that we just fine-tuned to the entire training set, which again has not happened yet in this exercise. And secondly, it uses then that model that applied to the entire training set to make predictions on the test set. So this is the first time the test set comes back into the exercise, just at the end. So again, notice that the test set was completely ignored during the training process, and that's how it should be. All right, so let's go ahead and do our final fit. We can collect the predictions. So here, when we collect predictions, we have 211 rows. That's because those are how many rows there were in the test set. Notice we have a column for strength GTEx, which was the actual value that was observed. And we had a .pred column that is the predicted value that this model is given. All right, so the next step here, we can check the metrics on the test sets. So the fit metrics on the test sets. For me, I'm getting on the test set an R-square of 0.81 and an RMSE of 3.11. Is anyone getting like very different, like the same? Okay, so we all got the same, which means that, yeah, we're still, even though our hyperparameters were slightly different, but in the end, when we trained this model on the entire training set, we still probably got the same model at the end. All right, so let's look into our fit metrics on the train set. And remember, the test set fit metrics are the ones that really reflect predictive ability of this model. The fit metrics on the train set are just an idea for us to understand how well the model fit our data. So if we just run this whole chunk, we get here R-square on the train set of 0.14 and 2.86 the RMSE. If we compare these fit metrics on the train set with the test set, So 286, 014. So a larger RMSE on the test set and a lower R squared on the test set. This is very typical, right? Because again, it would make sense that your model is predicting better the data that it has already seen during training, right? It's again, like if on the exam, I gave you some questions that were previously on quizzes. You probably got those right because you already saw them before. And even if you missed them the first time, you were able to redo them again and get them right the second time. But there were some new questions on the exam that I had not asked you before, and maybe you got those right as well, but maybe you didn't because you had not seen them before. All right, so this is the same thing here, is you would expect all of these models to have better fit metrics on the train set because they saw that data when they were being trained. So they had a chance of learning those patterns. And then on the test set, which is completely new data, they normally would still perform, but probably not as well as on the train sets. That's what we're seeing here. All right, and then we're gonna do our predicted by observed plots. Again, regardless of how simple or complex a machine learning model is, you should always expect to see a predicted by observed plots. This is what we're seeing. So I'm seeing, well, I guess, what do you notice here that is a little bit different from the previous model?
The points are parallel to each other.
Yes, we have 1, 2, 3, 4 parallel lines, right? Why do you think that is? Any guesses? Because just as a reminder, we did not see these parallel line patterns for the previous model, for the ElasticNet model. Why do you think we're seeing that on this model? Shay, you have a guess?
Yeah, I mean, my guess would be based on how trees work. You're essentially bringing data into the splits because of that. Whenever you're in that area of the split, you're essentially going to always have the same value.
Exactly. Yes. Thanks, Shay. Yeah, so let's see. I think yeah. We're gonna do the actual, we're gonna plot the actual tree for us to look into. And when we get there, I think it's gonna make more sense. So for now, let's just pin this and I'll return to this on the last chunk. And I'm gonna show you exactly what Shay explained in words, but I think it's easier to show with a plot than to just explain using words. All right, so another thing that is very common, regardless of the machine learning model, is to get a variable importance plot, which for ElasticNet, that was basically the magnitude of the slope for each variable, right? Because again, ElasticNet was just a like a linear model with many x variables, each one of them having a slope. And so the magnitude of that slope, the larger was the magnitude, the larger was the importance. For conditional inference tree, that's not how it works. So conditional inference tree, if you remember, there's going to be this iterative process of selecting one variable and doing a binary split. Selecting a variable, doing a binary split. Variables that appear on top are more important than variables that come after. So if you just run this, this chunk here, you're going to see that there are really two variables only that show up. So mean solar radiation in July and mean vapor pressure deficit in June. And then everything else doesn't have any value of importance. Why do you think that is? Any guesses? Well, we can go into our next chunk where we actually see the tree, and I think that's gonna help you understand why. All right, so again, conditional inference tree, one of the benefits is that it gives you one model, one tree model that you can look and interpret, right? Which is not gonna be the case with random forest, which is our next exercise. So let's go ahead and actually plot our single tree model from this training process. So we're gonna start with our final spec object. So the final spec, again, is where we trained on the entire training set. To pull this fit, we're gonna use a function called fit, which is coming from Parsnip, where we're basically gonna tell our formula again. So that was strength underscore gtex explained by dot. Give it a comma, break line. Let's give the data that we're using here. So we need to give both the initial data set and also the prepped data set. So we're gonna use here a function called, so well, let me show you, let me break this a little bit more just to explain you what's going on. So if we just get the weather prep, which is the prepped data set, we get basically, this is the train data with the recipe applied to it. That's what weather prep is. And then we also have weather, which is the data set that has all the rows, including training and testing as well. So here we're gonna basically give the entire data set with our train prep data as well. We're gonna use the function bake here, and then we give the weather prep first. And then we give the weather afterwards. And if I run just this part, the bake part, basically what happens is that it applies all the recipe steps to the entire weather data, which again, we have not done that yet. We have split that into training and testing, and we've been working just with the training set. So now we basically baked the entire weather data, which means apply the recipe that we had initially applied only to the training sets. This object here has a component that is called fit. So for us to pull that, I want to use the $$ fit nomenclature. So this basically, imagine that this dot is all the outcome from this. And then we're just subsampling that object by pulling out the fit from this model. So we get basically the actual fit. So this is what a party kit object will look like. This is the fitted model to the entire set. And then we just plug that into a function called plot, which is going to plot the tree for us. Okay, so this is actually something interesting that we can talk about. So, okay, the first thing is, how would you interpret this plot? So mean solar radiation in July had a highly significant p-value and therefore entered the model. And then it was split into two levels or two categories. So if that mean solar radiation in July was greater than 398.2, you came to the right. If it was lower than that same value, you went to the left. If it was lower than value and went to the left, then a new split also happened, which was the vapor pressure June, which also has a very low p-value, and then it splits into, if that vapor pressure was less than 2,130, then it came to the left, and if it was more than that, it came to the right. So a couple of things I want to highlight here. As we're seeing, and also the terminal nodes here, even though it's not showing up, but on the y-axis of the terminal nodes, this is strength. So it seems like, at least looking at these box plots, that the highest strength was observed when you had a lower solar radiation in July and a higher vapor pressure in June. This is it seems that to me that this median of this box plot is higher than the others. And then you had lower when either the solar radiation in July was higher than 398, or sorry, was lower than 398, or if it was higher and the vapor pressure was lower than 2,130. That's how we would interpret this plot. Now, why on our variable importance, we only had those two variables there? Basically, because those were the only variables that entered the model. That's the reason why. None of the other variables enter the model, so they have no importance. And then you can notice that solar radiation July, because it was the first variable to enter the model, it's the most important. So on CIT models, variables that appear on top would have would be more important than variables that come afterwards. Now, something that's interesting, and I guess I was not expecting it, but since it came up, let's talk about it. So as Shay was saying, we have those parallel lines on the predicted by observed because we only have, in this tree, we're seeing only three terminal nodes, meaning that all observations are going to fall into one of these nodes, right? And then if whichever strength value you got, but if it falls into these categories and it gets into one of these terminal nodes, the predicted value that the model gives is the mean of that box plot. Even though, so this distribution, this box plot is a distribution on the training set of the variables that fell into that condition. But when you use the model to make a prediction, it will predict the mean of that box plot for each one of those terminal nodes. And that's why we see those streaks on the predicted by observed. So if we come back here to this plot, notice that we have variability on the y-axis, I'm sorry, on the x-axis, which is the actual observed. So we have a lot of variability on the observed value for strength. But when we look on the predicted, it's a fixed value. Again, this is because of how this model works. If we would have wanted to get a better predictive ability here, we would have to use a model that had more terminal nodes, because then each terminal node would be a horizontal line here. So we need to break that down a little bit further. However, based on our training, we got only, well, on this plot, we have 4 horizontal streaks, because at least when we applied this model to the training sets, which is what this is doing, the model gave us 4 terminal nodes in the end, which is curious because when we check this plot, we only have 3. And the difference here is related to the fact that this predicted by observed, we're basically fitting the model to the training set only and making a prediction on the test for this plot. Whereas on this last plot, we're actually fitting the model to the entire data set, all 698 rows, not just the training. So we're getting a slightly different model when we train to the whole set as compared to training just, or to running the model just on the train sets. And I wonder here if we, so I'm trying to think of if we can do an on-the-fly change here. If we were to specify the data to be just our training sets. So let me go back on our training step and just see what would be the object that we need to specify. I think it would be another train. Maybe we can try just using weather train, just to play around and see if that would give us a model with 4 terminal nodes. So if we just give here weather train, and I think we're probably gonna have to, yeah, weather train here. Let's try this. Let me try to bake this and make sure it gives us what I was expecting. Yeah, so we can try this instead. Fitting just on the train set instead of the whole set, and see if we get 4, yeah. Okay, so we do get 4 terminal nodes if we fit just at the train set, which this is the reason why we were getting 4 streak lines on the predicted by observed. All right, I know that like, you know, we're using different data sets in different points, and this can be confusing. So I want to say this one more time, slowly, and then I want to open up to see if you understood. If you have any questions, I'll be glad to help you out to understand. All right. So on the predicted by observed on this plot, if we go back to the final fit, which is what we're putting here, the final fit, let me go back to that chunk, uses the function last fit, which basically does 2 things. It applies your train model to the entire training set. So not training plus testing, just training. And then uses that model to make a prediction on the test set. That's what last fit does for you. Right? And then when we do the predicted by observed plot, which is this, we're basically doing exactly that. We're using the model that we already found the best hyperparameter values, using those values and applying that just to the train set and training that model, and then using that model to make predictions on the test sets. Therefore, what you're seeing here on the x-axis, strength is a strength of those strength values are only for the test sets. But then the predicted values are coming from a model that was trained on the train set. So it's a little bit of some moving parts here. In other words, we're seeing 4 streaks here because when applying the best hyperparameter values to the entire train set, we got a model that had 4 terminal nodes in the end, which is now the one that we're seeing right here. However, earlier we were not seeing these 4 terminal nodes, we were seeing 3. The reason for that is because earlier on this code, I just had the weather data set here. And the weather data set has all 698 rows that include both training and testing. As you can see, one of the limitations of this model is that it is highly sensitive to the data that you use. And therefore, you could get a different model, just like we're getting here, depending on whether you're creating the final plot based just on the train sets or on the entirety of training and testing together. But anyways, that's basically what we're getting, a slightly different models here. This would, if you think about it, on the ElasticNet, we didn't have a plot like this, so we didn't do this specific chunk with ElasticNet. But on ElasticNet, what could have happened maybe is if you do your final assessment based only on the model fitted training or the model fitted the entire data set, what could happen potentially is maybe some of those slopes for each one of the variables could change a little bit, not a whole lot. In this case, we're really getting a different model with different breaks, even different variables if you notice. So here now we have vapor pressure in May as the most important, and then solar radiation in August and day length in September. So again, one of the cons of this model is that it's very sensitive to the data that you use to train it. So maybe if you come back and collect more data next year and you bring into this data set to update the model, it will most likely give you a different model in the end, which is a limitation, right? We do want models that are really robust that, they will get updated and improve over time, but not like switching back and forth between what it is every time you bring slightly new, different data. All right, so any questions about this? If you're confused, please let me know either now or later, because as you know, we're going to have a final exam. So some questions related to these things are going to come up. I do want to make sure you understand them.
Yeah, Dr. Bestos.
Yes.
I'm confused. So can you go over it again? Thank you.
So can you tell me more specifically what you're confused about so I can focus on that?
The middle part. So you mentioned that this model is sensitive to the data, like the data that we're giving. I couldn't understand the middle part of what you just said. So my question is, since it is changing, why are we for the important variable selection, why are we getting two variables uh, compared to the four nodes? Like in the last chunk, we're getting that there are like three important variables, but when we go to uh, the previous chunk, why are we getting two?
So the answer is right here, because I did not change this code to use only the training. So I changed the last chunk to use just the training, but not the previous one. So if you come here and you do apply that to just the train by this, we should see those three variables there. Yeah, it was just because I did not. So maybe I should have changed here and on the next chunk so you could see like the continuity of it. But I guess the main takeaway is that if you use just a training set, or if you use the whole data set, including training and testing for your final model, in this case, we're getting a different model based just on changing the data, bringing the testing to it as well. Yeah.
So for the sake,
Mhm.
sorry, go ahead.
No, go ahead.
So for the sake of consistency, shouldn't we use both the training data set in this important variable selection and pre-plotting?
Yeah, I mean I've seen it makes sense to use the training here, right? Because that was how you developed your model. Sometimes people bring the entire data set at the end to really have more, have a model that sees the whole data now that you've already. So let me just take one step back here. Normally, by doing this, it would not change your model significantly with other model types. In this case, it is changing because CIT is very sensitive to the data that it uses to train. We did all the training just on the training set, and we did the model fit metrics based on the test set that were completely separated at that point, right? Most of the time, you would definitely see people using the train here to show your important variables and your final plot as well. I've seen people also using the whole data set, but I think that's a great point. I think as a best practice, we should probably be using just a train at this level as well. In this case, we see that whether we use training or we use the entire data set, it is giving a different model. So that's up for discussion, which probably would not have been such a strong difference for other model types. But yeah, I think we should keep here the training sets when we're checking these models.
Okay, thank you.
Yeah, thank you. All right. Any other questions before we finalize this exercise? Okay, so if you do use the package, the CIT model, and you want a nicer tree than this, there is another package in R that has nothing to do with machine learning itself. It's just a package to make CIT plots looking nicer, which is called ggparty. I left you here some resources for that. So there's going to be a lot of functions. So here we're making the plot just by calling this function plot. If you use ggparty, it's going to use a ggplot type of functions for you to create a nicer tree and having more control over how the tree looks like. So if you want to, you're going to have control to basically everything about this tree. So that's just going to leave this resource for you if you're interested. And that wraps up this exercise. So in this exercise, we covered conditional inference tree algorithm. We talked about the pros and cons. Knowing pros and cons of these models is a really good question for an exam, just as a and advice. We set up a machine learning workflow to train this model. We use recipes to process the data, our samples to split the data. We use iterative search again, or I guess the first time in this exercise. On the previous one, we used a fixed grid search. Now we use iterative search to find the best values of max depth and mean criterion. We use tenfold cross-validation here as the resampling method to train the model on the training set by further splitting into folds, and each fold having a training and assessment set. We use both the R-squared and RMSE metrics to select the best model. And once that was determined, we predicted the test sets and explored variable importance. And especially, we had this plot here, which this plot, as you're going to see on random forest, we're not going to have a plot like this. Random forest does not have a single model for you to interpret. And then finally, we evaluated with predicted by observed, and then R-squared and RMSE metrics on the test set, variable importance, and the tree plots. All right, so we just finished this. Let's go ahead and come on your Git pane here. Let's stage your code, especially. Then let's commit. You can say something like finished CIT or whatever else you want to do. Commit, and close that, and then push. So now all of your code should be reflected on your GitHub as well as in your local machine. All right, once you do that, we should be good to close this exercise. I think this may be a good point for us to have a break. However, before you go on a break, I do want to ask you that I sent you all an email earlier today asking you to create a whole new GitHub project or repo and then project. And I share with you a script. So that new partial script for random forest is on our 2025 DSA GitHub. So go ahead and create that whole process, move the script into code, and then also copy and paste the data that we just used on the previous exercise into the data folder of this new exercise as well. With that, I'm going to give you a 5-minute break, and then once when you come back, then we'll start the random forest exercise.
Dr. Bistar,
Yes,
can I ask you a question now?
sure.
Since you mentioned about final exam, so is it going to be the same format as the midterm exam?
Yeah, I may
Okay.
have more like less written. I'm still gonna have some written questions or questions with written response, but fewer than in the midterm. It's just so you can get a grade faster. Because really what slows me down is grading the written responses. So yeah, but very similar format. So you know that's the again is the way that I do exams. I try to ask questions that are things that are really important that we've done a lot in class, that we stressed a lot in class. So
Okay, and it's going to be a closed book exam.
it's going to be closed book. Yeah.
Okay. So we will have to like memorize important functions, like we saw in the midterm exams, there were like fill in the blanks where you blanked out a part of a function, and we had to answer those, like write down those. So are we going to see same kind of questions?
We're going to have some code questions as well like that. Yeah. But also like if you, at least the questions on the exam, of course, like you had to you had to know the function, but at the same time, like if by looking at the context of the code, I think you could kind of guess as well from like just intuition of what should be where and what name. You know, so it's not like I was asking you to give me a function that had no context around it for you to understand it. So those are the types of coding questions that you could expect on the final.
Okay, thank you. I don't know. a lot of course classes I've taken, the instructor gives like a study guide for a final exam. So I'm wondering if you're gonna get any study guide or directions on how to prepare for the final exam.
I have not prepared a study guide, but it's still the same as I told you all. So if it's something that's on the lecture, it's fair game. If it's something that's on a script, like a comment that I made on a script for you all, that's fair game. You know, and functions that we use a lot. Like I'm not gonna ask you something that we use once, but it's something that we use a lot. I would expect you to be familiar with that.
All right, thank you.
It's- All right, so let's start our random forest exercise. Please go ahead and launch your RStudio project for this exercise. And let's get going. Okay, so our learning objectives for this are going to be pretty similar. Of course, changing the model, but again, I want you to notice how we're using an otherwise very similar workflow. We're just going to be changing a few things here to make it work for random forest. So basically, we're going to start off talking about the random forest algorithm, how it works, and why it is one of the most used and popular machine learning algorithms in any science. Then we're going to use our same framework to do the 3 steps, right? So what are the 3 steps here? Pre-process data, train the model, in this case, a random forest model, and then evaluate model predictability, just like before. And then I'm going to throw one new thing here for us, which is going to be to select the best model within 1% loss. So this is going to be yet another way of us selecting models. We saw already selecting the best, just the single best, selecting the best within 1 standard error, and now we're going to see selecting the best within 1% loss of the top models. All right, so quick intro here. We already talked a lot about multicollinearity being an issue, and first, what that is, right? A great question for exam, what is multicollinearity? And then we know that it could be an issue because it makes models less stable, less reliable, and it just adds some noise to our understanding of however your predictor variables are impacting your predicted variable. We talked about methods of overcoming multicollinearity with, again, dimensionality reduction. We're using PCA is one of the most used ways. And we can also do variable selection, again, either by hand, meaning you using your expert knowledge to determine what should be in the model, what should not. Also by using different models. Not all machine learning models handle multicollinearity well, but some of them do on different ways. Today we're gonna explore random forest, which has its own way of handling multicollinearity. It's a different way from before. So let's just quickly recap. ElasticNet handles multicollinearity by finding variables that are correlated and basically forces one of them to have a zero slope on the model by managing both L1 and L2 penalties. Conditional inference tree handles multicollinearity because it truly never evaluates all variables together. It evaluates predictor variables one by one at each one of the splits. So it's always doing like a strength by one weather variable in our case, and then strength by another one, and strength by another one, and then getting the p-value of each one of them, choosing the lowest p-value to keep moving forward. So although it is a multivariate analysis, but it never really sees all variables together when it's doing the linear regression part of the model. So that's how it handles multicollinearity, by avoiding having multicollinear variables in a given modeling step. Now, random forest also handles multicollinearity, but in a different way. We're going to see how that works in a second. All right, so random forest, again, is a very popular, perhaps one of the most used machine learning algorithms. It is a supervised machine learning algorithm. You should know what I mean by that. I'm going to tell you now. Great question for exam. Supervised means that you're giving it the y variable. You're telling it what is the answer that you're looking for, and then it tries to model the x variables to explain your y variable. On the other side, k-means is an unsupervised model. If you go back to that code, you're going to see you did not provide a y variable to k-means. You just gave all of your x variables and you asked, create groups of a given size for me, or create a given number of groups for me based on this data. So unsupervised, you do not give a y variable. Supervised, you do give a y variable. So all the models that we ran, machine learning models we trained until now, ElasticNet, conditional inference tree, and now random forest are all supervised because we all gave the y variable on the model formula. And it is a very, so coming back to random forest, it is a very robust model out of the box or off the shelf that we can definitely fine tune it, and we will fine tune it, but it normally achieves pretty good predictive ability on test sets, even if you don't fine tune it. And there is a reason for that. We're going to see why. It's still highly recommended you do fine tune it, but I'm just saying that any of the other models, if you do not fine tune it, you're really in the dark. You don't know how much more you could improve on those models if you were to fine tune your hyperparameters. With random forest, it's pretty stable right off the shelf, meaning even if you do not do hyperparameter fine tuning, it's still going to be a very reliable option. Now, the power of random forest, the reason why it is so robust and the reason why it's so popular is because of two random processes that it implements. The first one is that it does a bootstrap aggregating, which is also called bagging, on the rows of the data set. And the second process is that it does a random selection of a subset of your columns of your predictor variables at each split. We're going to talk again, we're going to dive down into each one of these steps here, but it's really important for you to understand how these are working, how these are at play, and how these actually are the power or what make random forest such a powerful algorithm. All right, so talking about the first one here, bootstrap aggregating or bagging. Can you also read that on the literature? So bagging trees basically are going to introduce this random component into the tree structure by having many trees on bootstrap copies of the training data. Let me re-say that in a different way. So a random forest is basically, the reason why it's called a forest is because it has a lot of trees, right? So it has many trees, that's why it's called a forest. And the way that each one of those trees are individually built is on each tree is built on a bootstrap sample of your training set. What does that mean? So bootstrap, if you remember, when we're doing bootstrap, let's say that on your training set, let's just make an easier number to think about. Let's say that your training set, you have 10 rows. You should have many more, and we have many more, but just to simplify, let's assume here that your training set has 10 rows. When we take a bootstrap sample of these 10 rows, we're basically going to create another subset, or not subset, but another set of data that is also going to have 10 rows, but it doesn't necessarily have to have the exact same rows as you started with. It could, for example, have 10 rows where out of the 10, 7 rows were individual data points from the 10 that you started, but other 3 are just a repetition of some other row that was already present. That's what Bootstrap is doing, is just keeping the same data size, but is sampling randomly from the original 10 in a way that you could get the same row on the original 10 2 times on the Bootstrap sample, or maybe even 3 times. So that's basically what Bootstrap sampling is doing. It's taking a subset, or it's taking a Bootstrap sample of your original training set. So it's going to have the same size, but it could have some rows repeated and some rows missing. That's what a Bootstrap sample is. And so the term bootstrap aggregating is that for each individual tree, it is given in a training set that is a bootstrap copy of your training set, which we just talked about what that means. And then it trains that tree on that specific bootstrap sample. And then the next tree is going to be another bootstrap sample. And each tree is going to have its own different bootstrap sample that's being trained on. In the end, when you have all these trees trained, they all saw a different part of the rows. None of them saw the same exact set of rows from the other. This is one of the ways that random forest is really powerful. Then the term bagging here, just to let you know. So bagging is basically a way to say that when you do ask for this forest to give you a prediction, it's just going to get an average prediction across all trees. So each tree that was trained on a different subset of their data is going to give a prediction. So if you have 1,000 trees, you get 1,000 predictions. But in the end, the algorithm basically bags all those predictions, or it aggregates all those predictions to give you one prediction. So if you give if you train a model and you know this model needs these variables to explain strength, and you give only those X variables, you do not give strength, and you ask for a prediction, it's going to give you just one prediction. But that one value that's given you as a prediction is an aggregated value of the prediction across the entire forest. So if you have 1,000 trees, you have 1,000 predictions that are averaged to give you one. That's what the aggregating part of bootstrap aggregating means. Okay, so that's the first random process that Random Forest implements, is doing bootstrap sample for each tree. So again, you have your whole training set. Each tree is going to see a bootstrap sample of the original training set, meaning that the bootstrap sample could have some of the original rows missing. It could have some of them duplicated. That's what bootstrap does. The other important random process here is that Random Forest uses a random subset of features at each split on each tree. So the way that this works is, so imagine on the first tree on this forest, you can kind of think of each one of those trees very similar to a conditional inference tree. It's still a very similar process. But the difference, well, there are a couple differences, but one of them is with CIT, you have one tree. With random forest, you have as many as you ask. So let's say you have 1,000 trees. So for each tree, let's think of the first tree on this forest. The first thing that happens is we get a bootstrap sample of a training set and give those rows to this tree. But then before we let the tree grow, we also do a sample on the number of columns in a random sample. So if you have 72 other variables, each tree is just going to see maybe a third of them. Or, I mean, they're going to see a subset of the columns. So maybe the first tree saw, 20 columns only. And then if you were to look into them, you would see that maybe you have like some that are in January, some that are in July, some are solar radiation, some are precipitation. But that first tree is not seeing the whole number of columns in this training set. Then you go, well, still on the first tree. This happens at each split. So on this first tree, on the first split, it is seeing the same number of bootstrap rows, but the number of columns is a random selection of columns for that split. And then let's say the first split chooses a variable and it splits into two. Now, each one of these other two new splits are seeing still the same number of bootstrap rows, but they're seeing a different number of columns randomly selected for each one of them. So taking one step back here and just saying this one more time. The first random process, the bootstrap sample, it happens once per tree. So it happens once for that single tree. And within those bootstrap number of rows, each split of the tree is seeing a subset of the columns. And that is just for the first tree. Now, when you move to the second tree, that you're training in the second tree, is going to see now a new subset of rows from the bootstrap samples. And each split on the second tree is also going to see a different subset of columns that are being evaluated at that split. These two things working together are what make random forest so robust. Because again, each tree is seeing a different version of our data, and each split in the tree is seeing a different set of predictor variables as well. Have a question? I'm seeing some confused faces. So I think I'm going to try to get to the end of this random subset of features part, and then I'll open up for questions because maybe some more text here is going to help you understand. So if you think about it, the number of features or columns or predictor variables that you let each split on each tree to see is a fine-tuning parameter. It's called mtry. So this is something we will train. So some typical values for this value of mtry. So again, mtry is the number of features you allow each split in each tree to see. Normally, the value of mtry is p divided by 3 for regression, like our case. So regression meaning our predicted variable is numerical. So we have p for us is the number of features total. We have, I think, 73. So the default mtry value would be 73 divided by 3, whatever that is. That would be the mtry value. That would be the number of columns that will be randomly selected at each split of each tree to assess. If we're doing classification, which we're not, but classification would be if our y variable is categorical, then the mtry is the square root of p. Now, because the algorithm randomly selects a bootstrap sample, meaning it's getting a random selection of rows and a random selection of columns at each one of the splits, a more diverse set of trees is produced, which then tends to lessen the tree correlation. So one issue that we may see is imagine that you were to just train a whole bunch of CITs, where the CIT is seeing the whole data set, the whole number of rows, the whole number of columns of the train sets. It is very likely that you're producing the same tree, right? Because they're all based on the same data, or maybe some slight variations that we just saw. But overall, you would have most of the time the same most important variables in place and having a very similar tree if you were to train 100 conditional inference trees separately, but always seeing the same rows and same columns. The power of random forest is that it is training out many trees, but each one of them is seeing a different version of our data. They're seeing a different row set from the bootstrap sample, and then each split is only being allowed to see certain columns, not all the columns at the same time. So they will be forced to only work with what they have. So tree 1 may be completely different from tree 2 and tree 3 and so on, because of these two processes working together. Random selection of rows with bootstrap, random selection of columns at each one of the splits of a tree. So in the end, when you ask for a prediction from this forest, each tree is giving a prediction. And maybe if you were to look at just one of those trees, it would be a horrible prediction. But because you have so many trees, they were all trained on a different version of our data, on average, they make a really good prediction. That's the power, again, of random forest, and that's how it works so well. All right, so then, well, before I start talking about hyperparameters, I just want to take a step here, take a moment here and ask if anyone has questions. I know you have, because this is a complex topic, so maybe I'm just so confusing that you just did not understand to have questions, which I hope is not the case, but yeah.
Dr. Vestas,
Yes.
so you mentioned that for regression, the default value for mtry is p over 3. So the 3, is it constant for all models or does it change?
What do you mean by models?
Sorry, for different data sets. I mean, this p over 3, this formula, does it remain constant for all data sets? Like, is it the same?
It's gonna be, so that's the recommendation, right? So if you think here, so if we were to set mtry, which again, mtry is the number of features that each split sees. That number would be, so we have here 73, I guess, so 73 by 3. Each split would see a random subset of 24 columns only. However, this number is, so this would be the default. If you just go and run a random forest and not train it, this would be the default that it would use. In our case, right? So with 73 features. But this value is trainable. We can further improve our model by finding the best value of mtry.
Okay, thank you.
Thank you. All right. So again, even though random forest is pretty robust off the shelf, but we can and should still train it. And again, our training, every time we're training a model, we're just changing some hyperparameter value that will allow the tree to be more complex or more simple, depending on the value of those hyperparameters. And this all comes back again to that bias variance trade-off. Remember that plot. It's a great plot to be on the XM as well. So random forest has also many hyperparameters that we can tune. Normally, you would see these in the literature. So the first one is number of trees in the forest. As the name says, is just how many individual trees you would allow that forest to grow. The other hyperparameter here is the number of features randomly selected at each split of each tree, which is called mtry. And then the other one is the minimum node size, which is basically the minimum number of observations to have in a node of a given tree for it to be split. We're going to talk about these three and how they impact the overall performance of the model. And then we'll actually get started with the training of the model. All right, so starting with number of trees. So normally what we want is a forest that has enough trees that stabilize the out-of-bag error. That's the OOB error. The out-of-bag error, let me just tell you what that is. So for each tree, as I told you, it's using a bootstrap sample of the training set. So if your training set has 10 rows, the bootstrap sample has 10 rows. But the bootstrap sample may have some samples that are duplicated and some that are completely missing. The ones that are missing are the out-of-bag samples. And so it trains on your bootstrap sample, but it knows which ones are not present on the bootstrap set. And then it makes a prediction on those. That's what the out-of-bag sample or out-of-bag error is. Okay, coming back to this plot. We want a forest that has enough trees to stabilize the air. So what we're seeing here, and also a good rule of thumb is to start with 10 times the number of features. So what we have 72 features, then we would start with about 720 trees in our forest. In this example here, which does not come from our data, but you see that your error on the y-axis decreases as you increase number of trees on the x-axis, but if it reaches a plateau here, right? So there is a, maybe, so this model here evaluated up to about 1,000 trees, but maybe it was already good enough at 500 trees. But how do you know that? How do you know what's the best level? By fine tuning, right? That is one of the hyperparameters we're going to fine tune is the number of trees. So in general, more trees are not going to hurt your model performance. But if you have an excessive number of trees in a very complex model, why would you go to 1,000 if you only need 500? This is especially important because the more number of trees you have, although it does not hurt model performance, it will hurt your computational time. If you ask for many more trees than what you need, it's going to take longer to train that model compared to if you were to bring that value down to a point of number of trees that did not hurt your error, but are still less trees than a very excessive number. So again, although number of trees does not hurt your model predictive ability, but it does hurt your computational demand to train the model. So we want to fine tune that mostly because of that. All right, next one we're going to fine tune is mtry. So mtry, again, is how many features each split in each tree is allowed to see. It helps to balance low tree correlation with reasonable predictive strength. Again, this makes sure that each tree or each split of each tree is seeing a different subset of variables, and therefore to create variability in the trees you're creating. Because again, if you were to give always the same exact set of rows and columns to all 1,000 trees, you would probably have 1,000 trees that are very similar, right? They're all being trained on the same data. They all are seeing the same data. Random forest is giving a different subset of rows and columns to each, a different subset of rows to the tree, and within the tree, a different subset of columns at each split, making that tree be very different from its neighboring tree or any other tree in that forest. So why do we have to fine tune this? So when we have fewer relevant predictors, then a higher value of mtry works better. Why is that? Imagine that in our 72 predictors, if we only had 3 that were really strongly correlated with strength and everything else is not. If you have a high value of mtry of, let's say, 50, it means that each split is going to see a random selection of 50 columns. The chance of you having one of your 3 highly important variables in a subset of 50 is high. So at least you're having that very important variable appearing most of the times in most splits of most trees. And so if you have a large number of variables, but only a very small subset of them are really important for you, but you don't know yet, then mtry should be big, because the chance of having those fewer set of highly important variables appearing for each split is going to be higher, making sure your trees are trained well. Now, on the other hand, if you have many variables that are highly important in explaining your predicted variable, then you want an mtry that is lower. You don't want the trees to see all of those very important variables all the time. You want to give different sets of important variables to different splits so they can create variability in the training process. Let's visualize that effect. So here we have, again, number of trees on the x-axis, out of bag error as our MSE on the y-axis. In each line here is a value of mtry. As you see here, if we give mtry, or in this case, right, this is just one example to show a visual assessment of this. It doesn't, these numbers are not special in any way, but an mtry of 2, meaning that each split of each tree is only seeing 2 variables, 2 predictor variables. We do see that overall pattern of increasing trees, decreasing error, but if you have very few number of variables being evaluated at each split, in this case 2, that error, even though it stabilizes, but it remains pretty high. Now, if you see other lines here that kind of almost converge here on the bottom, but the line that has the lowest error is where mtry was 21. And then there's one that mtry is 80, which is not the best. So as you can see, there is a sweet spot of mtry. It's not always high is going to be better, always low is going to be better. It's going to depend on the data, and it's probably going to fluctuate as well. Right? So here in this case, mtry of 21, meaning that for each tree, on each split, it was evaluating 21 random features of your data. That was the best for this data set. Yeah, sorry, Fu.
So for each tree, there will be one important predictor variable, right? But when we are selecting the number of mtry, there will be split. So for each split, there will be, I mean, for each split, there will be another predictor variable, right? I mean, what I'm trying to say is that for the split, how many predictor variable will be there, and how the model is going to select only one from that. I think my question is confusing.
Okay. Well, I'll try to explain, and if I don't get it, let me know. So, okay, so let's just let me repeat one step. So the first random process, which is a bootstrap of the rows, is apply once for that tree. It's just going to be different for the next tree and then the next tree. But within a tree, the subset of random rows is the same. But so imagine you have a subset, I mean, your training, let's say your training set has 10 rows. You do a bootstrap sample of that. The bootstrap sample is also going to have 10 rows, but it could be that some are replicated, some are missing from the bootstrap sample. That's what goes into that first tree. Now, this first tree still has 72 columns. So mtry is the value that's going to determine on each split how many and which one of those 72 columns are evaluated. So let's say that at the first split, mtry is going to be, for a given model, mtry is fixed, right? So mtry is going to be, let's say, 3. Meaning that if mtry is 3 for that first tree, the first split is going to see 10 rows, but only 3 columns of the 73 total. And that is a random selection of which 3 he sees. So it only evaluates those three columns to decide which one of the 3 are the best one, and then use that to make a split. And that process of selecting the best one and making a split is very similar to the conditional inference tree. But now once it makes a break, it splits again. Now those 2 splits, each one of them individually, are also going to see another random subset of the columns. So now maybe the columns that we're seeing on the first split are not even the same, most likely will not be the same as the columns seen on the other 2 splits. And if it keeps breaking down, making a very complex tree, each split is going to see just a subset of the columns. Does that make sense? Does that help?
Yes. So at the end, how many important predictor variable will there? There will be only one, right? For each tree.
It depends on, okay, so right now we're talking about, so number of trees. Within a tree, what is the mtry? That has not determined how many breaks the tree can have. We have not talked about that. That is actually what I'm going to be talking about next on the node size. So now what controls how deep a tree is going to be is the node size. So let's go to that, and maybe that's going to help you with that. But in the end, you can have multiple splits, meaning that you have many variables in that tree, in each individual tree in the forest. So node size is another hyperparameter that we can fine tune here. And that refers to the minimum number of observations in a node for it to be split. Meaning that if you create very complex trees, the number of observations at the bottom is going to be very small, right? Like imagine that you have 10 rows, that breaks down into 7 rows to the left, 3 to the right. And so the 3 is maybe not going to break out anymore because it has so few rows, but the 7 may break another time. So it may break where the 7 now breaks into 4 and 3 again. So we have 3 terminal nodes. So node size is that number that will say, well, if this number, if the node size, if the number of observations in a given node is greater than this threshold, then it is allowed to break further. But if it's smaller than this threshold, it's not allowed to break further. So the node size will control how many breaks there is, and therefore how many variables are important for that given tree. So here, larger number of node size is going to grow simpler individual trees. So imagine that I say, well, my training set has 10 rows, and I have the nodes, the minimum node size of 5. Meaning that maybe my 10 rows are going to break once, maybe you have 7 coming to one side and 3 to the other. If my minimum node size here that I'm controlling is 5, then the node that has 3 is not going to be allowed to break anymore. The node with 7 may break again, but the one that has 3 is not going to break anymore. That's what node size is doing. It's controlling whether or not a node can further break into new nodes, depending on how many observations it has. If computation time is a concern, then you can often decrease the runtime that it takes to run that model substantially by increasing the node size and have only marginal impacts to your error estimates. Let's see that sentence in a plot. So here we're seeing minimum node size on the x-axis, and then on the first plot, the percent growth in the error estimates, and on the second plot, the reduction in runtime. So we see that if we increase the minimum node size from 5 to 20, we increase the error, but if you look at the y-axis scale, we're going from 0 to 3% increase in the error, which is not bad. However, by changing the same minimum node size from about 3 to 20, we're significantly decreasing runtime in about 50%. So node size is one hyperparameter that can help us to make our models run more efficiently if that becomes a concern. All right, so we talked about the 2 random processes that help random forest be very robust. One is a random bootstrap sample of the rows for each tree. The other is the random subset of columns for each split in each tree. Then we also talked about number of trees, mtry, and node size as the main hyperparameters that we can evaluate. And I think before I move further, any questions about this? All right. So then how do we grow an individual tree? So think again that random forest is a collection of trees, and that's what's called a forest. So how do we grow an individual tree first? So each individual tree will grow based on the node size. So the smaller nodes, minimum node sizes are going to allow for trees that are going to be deeper. So it grows based on the node size, on the bootstrap sample of the rows, and then evaluating a given number of random columns at each split. That's how a given tree is going to work, is going to grow. On each split, the selected variable and its binary split are chosen by evaluating many random splits, selecting the one that minimizes the error. I have this figure here to kind of show you that. So imagine that you have first tree, first split. It basically is assessing here one of the variables. In this case here, the variable on the x-axis is socioeconomic status index. So nothing to do with what we're doing, but just to depict what's going on. So for that variable that was selected as split, is going to choose a random vertical red line here. Choose a random value of that x variable, and then assess what's the error left on both sides, and then choose another random, what's the error, another random, that's what's the error, and seeing which random split of that X variable creates the lowest error on both sides, and that's how it determines which point of that variable is going to be used to make the splits. So if you remember for CIT, we had like, let's say, solar radiation in July. If it was more than this value, it was coming to the right. If it was less than this value, it was coming to the left. That value that it found, at least for random forest, is doing that using this random iteration process at each one of the splits until it finds a breakpoint on the X variable that optimizes or that minimizes the error of both sides. All right, so that's how we build one tree. Now, from a tree to a forest, that's what random forest is, right? So random forest is just an ensemble of many trees, where again, each individual tree is made up of a bootstrap sample of the rows, and then within that tree, each split is a random sample of the columns. And so the forest grows by training each tree and just combining all them into one algorithm. And when you make a prediction, each tree is going to give you a predicted value. I mean, it's not going to give you, it's going to create a predicted value. But the prediction that we get from the model is just an aggregation, in our case, an average, because we're doing regression, an average of the predicted value across all the trees. The model takes an average and gives you one predicted value for your single observation. Some pros and cons of random forests. So starting with the pros, it has pretty good performance even without tuning. That is maybe one of the models, one of the machine learning models that is more robust because, again, of those two random processes. It has pretty good performance off the shelf. It is simple to train. It does not have a lot of hyperparameters. It can model nonlinear relationships because it is a tree. So if you remember on that example that we showed on the CIT lecture, that the more breaks and more nodes you allow the tree to have, the better it can fit the shape of something that's numerical that can be linear or nonlinear. Random forest has the same pro here. Random forest can be used with both numerical and categorical response variables. In our case, we're using, again, a numerical response variable, strength, but if we had a categorical response variable, it would work as well. It handles NAs pretty well. So some algorithms do not handle NAs at all. You have to impute data. Tree-based algorithms normally handle NAs pretty well. And the reason why it's the most popular machine learning algorithm is because it offers great balance of variance and bias. It has a good balance of variance because it grows many trees. So imagine that a given tree, like we saw with CIT, can have high variance. Because if you change the data that you train it, it may change the model completely. Not completely, but to some extent, it's going to change the model. Random forest, individual trees have high variance. But because you create many trees and then you average them, you decrease that variance when you take the average. And it also balances the bias because you're averaging over them. So by growing many trees that are all on their own, they have high variance. But when you average over them, you reduce the variance and have a better balance between that and bias. One of the cons of random forest is that it's not going to be as interpretable as previous models. So CIT, we had one tree and that was it. We could look into the tree, we could see the variables, we could see the breakpoints. In random forest, you may have 1,000 trees. You're not going to show 1,000 trees in the paper, right? So there is no single model that you can show from random forest. So we have to interpret it from using different ways rather than just looking at a model. So again, remember that trade-off between model complexity and predictive ability is a pretty common trade-off. So ElasticNet is perhaps one of the most interpretable models because you have the coefficient of a regression, in that case, a slope. Very easy to interpret as slope, right? 1 unit change of that X variable for a change of the slope on your Y variable. Pretty simple interpretation. CIT, conditional inference tree, is also pretty simple to interpret. Random forest, not as simple. You don't have a single model or even model coefficients that you can look into and make sense of. It's 1,000 trees, and each tree is different. Each tree has different variables, different breakpoints. It's very difficult to interpret from that perspective. So we have to be more, we have to use different ways of actually interpreting random forests. All right, before we start with the coding, any questions? All right, I don't hear any, so let's begin here. I don't think we'll be able to finish today, but at least we'll get started, and then next class we'll finish it. All right, so I left you here one package for you to install. It's called Ranger. It is one of the packages in R that does random forest. So install it and then comment off or delete that line of code. After that, make sure you load all the other packages by playing the chunk. We're gonna import our data here. So import the weather data. At this time, you're already pretty used to it. 698 rows, 75 columns. This is our entire data set. I left you here a lot of the code already because we have already coded that individually before. So we already know this, but we're going to do the weather split. So just run with the set seed as well. And notice that we're doing the strata by strength to make sure that the distribution of strength across testing and training is similar. Now we are going to pull our weather train on the next chunk. Go ahead and run it. On the train set, we have 487 rows, just like before. Now let's do the weather test. Just pull the test set. We have 211 rows, just like before. And again, I left you this plot here to check the distribution of strength across test and training. It should be the same plot as you have before because we set seed. So still we see that their distribution is pretty close, and that is a function of us doing the stratify sampling based on this variable. So now we put our test set aside and just keep training with our train sets. As you know, we need to do some steps here on the pre-processing. We're going to create a recipe for that. If we go to this link here that I left you on all three scripts to check what are the processing steps we need for different models. I always encourage you to do that and follow those recommendations. If we come here, the model we're going to be training is Rand Forest. That's the model type. We see that it's really required this step here. If you go all the way up, this step is imputation. Imputation is for when you have NAs in your data, you have to input those values. However, there is a superscript 2 here, and if you go to the below the table and read that, it explains that theoretically, any tree-based models do not require imputation. However, many tree ensemble implementation do require imputation. It says here specifically that tree-based boosting methods, we are using a bagging method. Another difference on trees is that some trees use a boosting method, which is going to be XGBoost, which you're going to learn after this. So for trees that have boosting methods, well, in this case here, it's talking about another step that is that of creating dummy variables. So it's just saying that while tree-based boosting methods generally do not require dummy variables, models using XGBoost engine do. So we're going to see this next. But basically, we're seeing here that imputation may be important for the random forest model. In our case, we do not have any NAs. We don't have to worry about imputing. So any of the other steps here are just either not needed or perhaps recommended but not required. So we just don't have to do much else other than what we have already been doing, which was just to remove variables that happen outside of the growing season. So I just left you the same recipe as before. You can go ahead and run it. Now we need to apply this recipe to our training set. So we're going to use the prep function to do that. And we see that it's being trained on our train set. As this word is now here, it was not here before we trained it, when we just had the recipe. All right, so model specification. We're going to need to specify the type of model, the engine, and also the mode. When we specify the mode is when that model can run both regression and classification models, like CIT was able to, and also Random Forest is able to. ElasticNet was not able to do a classification model type, so we did not specify mode for ElasticNet. ElasticNet only works with regression, so continuous y variables. And then the Random Forest hyperparameters that we're going to have here are going to be trees is the number of trees in the forest. mtry is the number of random features or columns that are sampled at each node split. And min_n is the minimum number of data points in a node that are required for the node to be split. Let's fine tune the first two here. We're not going to fine tune min_n in this exercise, but you're encouraged to do that on your side if you're applying this to your data. And this is mostly just because of time constraints. It's going to take a lot longer to fine tune all three. So below here, we're going to do our model specification, which is the first time on the script that you're going to have to code. So notice that everything up until this point was the same. It's just that we're going to start changing things at the model specification level. So if you come after that first comment, we're going to specify Random Forest as our model type. So the function is rand_forest. And this is also where those two hyperparameters live. So they are model type level hyperparameters. So we're going to say here trees. We're going to train the number of trees. We're going to put the function tune. Notice again, just kind of making a connection with the previous script. If you were just to come here and give a number and say 10, great. It is going to run that model for you. It's not going to train that hyperparameter for you if you give a fixed number. If you do, however, put the placeholder function of tune, is going to fine tune that for us. The next one is mtry, so the number of columns at each split. We're going to also add a tune here, so it does fine tuning for us. Now give it a pipe, come after the next comment. Again, there is a model type that is a general class. So Random Forest is the general class, but there are different engines that we can use in R to run that model. The engine we're going to use is going to be that other package Ranger, which you just installed. So set engine, we're going to say Ranger. If you check our code across, on Stack Overflow or other sources, you may see they're using a different engine for Random Forest. Again, just means they're using the implementation from a different package. The engine just relates to the package being used behind the scenes. Then give a pipe. We're going to specify the mode. So we're going to say set_mode. And then regression. Again, this is because Random Forest handles both regression and classification. We're just making clear that we're doing regression in this case because our y variable is continuous. Around that, we have our specification. Now we're going to do the hyperparameter fine tuning. So for this, we're going to need our specification, our recipe, and our resampling strategy, which we don't have yet. Now, I do want to make a connection here again with the CIT model. Remember that CIT had one hyperparameter at the level of the model and one at the level at the engine. Because of that, we had to do one extra step for that hyperparameter at the level of the engine to set the levels that would be searched in the grid. Here with Random Forest, both of hyperparameters are at the level of the model. Both of them are here on this level. We don't have anything on the engine level. Therefore, we can skip one of the steps that were required for CIT that here we don't have. Also, before we use a 10-fold cross-validation, on my computer, it was taking beyond 10 minutes to run the grid search with 10-fold cross-validation. So because we're in class, I want to remove, or I want to reduce that time. I reduced the number of folds to 5 instead of 10, just for that. But I would highly recommend that when you do on your side, do 10, at least 10 folds of your data. So go ahead and run this chunk so we can have it implemented. As you can see, now we have 5 folds, where each one of the folds has 80% of the data on training, 20% on assessments. We're going to use simulated annealing again. We already talked about this process on the previous class, so I'm just going to skip that explanation here. And this is where we're going to fine tune it. So this is going to take probably 5 minutes, and we don't have that time right now. So for now, I'm going to reduce this to 10, just to not take as long. Again, this is a number that I probably recommend 100 at least. So when you do have the time, go ahead and run your larger number of iterations. Go ahead and run this chunk as well. So it's gonna get started. As before with simulated annealing, we already saw this. It's gonna look for a combination of hyperparameters to get started, and then it's going to iterate over that space using simulated annealing and navigating through that space. So if you open your console, you're gonna see that it started with an RMSE of 2.86. On my second run, it found a new best of 285. It's going to be navigating for 10 times on this case until it finishes running, and then it takes the best combination of trees and mtry as the one that had lowest RMSE. I think when I was running 50 iterations when I was making this exercise. And at least on my side, I think it found the best combination and iteration like 45. So there's definitely value for us to allow this to keep going further. But again, for time constraints in class, that's why we reduced it to 10. So on my side, it just found a new best on the 8th iteration. And that's it.
What did run 50?
You did run 15?
I did run 50? Oh, you say you're, I see.
Yeah, I did 10. Yeah.
Yeah, excuse me, Professor.
Yes.
I'm 50 and my number is 25. The mtry number.
Okay, so I have not pulled that yet. We'll get there in a second. Yeah. Because here I think it's here is just showing for the second fold. So it's not the overall recommendation yet. Okay, so let's look into that RMSE grid plot that we saw before. This is how it looks like. So basically here RMSE, we want the lowest. So the darker points here looks like around mtry of 31, I guess, and number of trees close to 600. That's what seems to be the best looking at RMSE. When we have only 10 iterations, again, you should have more on your side outside of class. Now looking at R square, we want the highest, right? So in this case, we're seeing the highest here on the 8th iteration, where it's using an mtry of about 31 and trees of just below 600.
That's a lot different.
Is a lot different. Yeah, maybe let's go ahead and pull those models actually, and really compare to see if we get different values or not. So let's go, and this one of the differences of this script is we're going to pull the best model using a different function. So we already used the single best, we already used the best within one standard error, and now we're going to use the best by percent loss. So if you add a pipe here on the grid results, we're going to use a function called select _best. So not that, select underscore by percent loss. We're gonna base that on the trees algorithm or trees hyperparameter. The metric that I will use is RMSE. And I want to write limit equals 2. This is how many percent losses you were accepting in this case. If we run that, I get a model with an mtry of 24 and 518 trees. How does that compare to y'all?
Totally different.
Different? Yeah, this is probably the fact that we only had 10 iterations. If we had more iterations, I would expect that we converge to the same value. What did you say? You ran 50? Okay.
25. Thank you.
So you got 25 mtry and number of trees? Okay, nice. All right, so those of you that ran 50 iterations, so can you say that again? Sorry, 20?
That's for MTRY 25.
So 25 mtry, 443 trees.
I ran 10, but I got the same.
Okay. Nice. Yes, Osman. The same as them?
I got that same number, 25 and 43.
Okay, awesome. Well, yeah, I don't know why I got, well, I got different because of that randomness of two things going on at each tree. And also we're doing that on a lot of models. So there's a lot of models going on, a lot of randomness happening behind the scenes, right? So I think that's what's causing some of the differences. If I had my iterations longer, I think I would have gotten the same as you all. All right, so let's do the same thing here on the R square. So we're gonna use the same function, select by percent loss, using the trees hyperparameter trees. Our metric being in this case RSQ for R square, and limit equals 2 again. So when I do that, well, on my side, I get a different answer now. I have 31 trees or 31 mtry and 573 trees. So in this case here, I'm getting a different, even on my side, I'm getting a different answer if I use RMSE or R square. On your sides, are you getting a different answer as well? Okay. Yeah, this is common. It could happen. I would say for us to use the R square as our metric to decide the number of trees. Because I only ran 10 here on my side, I'm going to use whatever number you all found here on to define the best value. So 24 tree or 443?
Yeah.
And 24 mtry. Okay, perfect. All right, I'm gonna just plug those numbers so mine match yours. 25. But you could use the function on your side like I had in the code previously. There is something missing from this code, which is the engine. And the reason why I left that missing is because we're gonna do one different step here. So we're gonna use the function set engine just like before. We're gonna call the Ranger engine, which is the name of the package. But then it has an argument we have not changed before, which is called importance. So I want to, importance equals to, I want to say permutation. So this is going to be one of the ways we're going to look into variable importance in this random forest model is by looking to the permutation. Make sure that you then add your pipe after that so it connects with the set mode, and then you can go ahead and run it. All right, so getting on our validation, I think I left you all the code in this chunk. It's just like as before, we're getting the last fit. So what does the last fit means? This is a great exam question. It basically does two things. It trains the optimal hyperparameters on the entire training set, and then uses that to predict on the test set. So if you do it and we collect the predictions, we're gonna have 211 rows because that's how many rows we have on the test set. Yes, Mark?
So I just wanted to share that I ran the 100 trees, I guess. I ran 100 iterations and the number is same for me,
Okay.
25 and 443.
35 or 25?
25.
25. Okay, awesome. Awesome. Thanks, Mark. Well, let me do all this. I know we're at the hour. I think, Amrinder, did you already open? Okay, thank you. So you can claim your attendance. If you need to go, you're welcome to go. I want to get to the end here because we just have a few more chunks, but I don't want to keep you if you have to go. So claim your attendance. If you have to go, you're welcome to leave. I'm gonna keep going and recording, and then you can catch up the last 5 minutes later if you have to go now. All right, so we can collect the metrics, which is on the test set. We see here that we have an R-square of 0.19 and an RMSE of 291. I think this is the best model yet. If I remember from the previous test set metrics, I think that those were lower metrics than these two. If we are curious and want to check the fit metrics on the train set, go ahead and run it. Look at that. On the train set, we have 95.95 R-square. Really, really high. And again, this is the reason why it's okay if you want to report your train set metrics. It could be useful to understand how well your model is explaining your data, but it's not a good measure of predictive ability. For that, you have to look into the fit metrics on the test set. Notice we have on the test set 0.19 R-square, and on the train set, we have 0.95, a very large difference. All right, so now we're gonna do our predicted by observed on the test set. Still looks kind of like the ones before. It may be getting a little bit closer to that one-to-one line, but not by a whole lot. And because, again, this is an R-square of 0.19. That's why it still looks like this. For variable importance, here in the case of random forest, we're using permutation. I want to explain to you quickly here what is permutation. So in a permutation-based variable importance, for each tree, the out-of-bag sample is passed down that tree and the prediction accuracy is recorded as is. And then what happens is that the values for each one of the variables used on that tree, so each X variable that was included in that given tree, the column of those variables is shuffled. And then it reruns the same model on that tree again and compares the accuracy without shuffling the predictor variables and shuffling the predictor variables. What happens here is if that predictor variable in that tree was important, if you shuffle it, you're gonna see a large increase in the error. Right? So imagine you have a column of like solar radiation in July being very important. Now you shuffle all those values randomly. If that variable was truly important, when you shuffle it, the model and retrain the model with the shuffle version, that model is going to have a lot lower accuracy than the one without shuffling. So if you do permutation, if you shuffle a column that is in the model, and then you retrain the model and the error increases significantly, it means that that variable was important. So that's what permutation is doing for each one of the columns that are in each one of the trees. And so the variables with the largest average decrease in accuracy after being permuted are the ones considered the most important. I left you all the code here. If you go ahead and run it for the variable importance, you're going to see that solar radiation in July was the most important. Solar radiation in August was second most important. Minimum temperature in June was also very important, and so on. As you see here, we have many variables. All variables in this case are going to have certain level of importance. In contrast to CIT, conditional inference tree, the only important variables are the ones that appear in that single tree. Now here we have about 500 trees, and each one of them has different variables. So when you shuffle each one of those variables, It's just assessing here which variables that after shuffling reduce the model accuracy significantly. This is what is going on here. All right, so a quick summary. Today we covered, well, we finished the CAT and then now we started and finished the random forest. So we covered the random forest algorithm. We set up a same workflow, just changing some parts of it to make sure that we're fitting the right model. We use recipes to process data, R samples to split the data. We use, again, iterative search to find the best combination of two hyperparameter values, the max depth and minimum criterion. We use 5-fold cross-validation. We could go back and train with 10-fold cross-validation to make sure we get more robust results. Use the fit metrics of R-square and RMSE to select the best model within 1% loss. And also then tested that model or evaluated that model using the test sets and its fit metrics as well. Evaluated all that with using some plots. Predicted by observed is important. Again, random forest, we do not have a single tree. We have, in this case, about 500 trees. So one way to interpret random forest models is you should always expect to see a predicted by observed plot and a variable importance at least. Those are the two things you're going to see from random forest models in the literature. All right, that's all I had. If anyone has questions, I'm going to stick around for another couple minutes. If not, and if you're still here with me, then you're dismissed, and I'll see you on Tuesday.
And Dr. Vistas,